Welcome back. So we just discussed how acoustic methods are state-of-the-art for assessing the discharge of large streams and rivers. But for small streams, often even Strawberry Creek, it can be difficult to insert a probe at the level it needs to be inserted to make a measurement of velocity. And so it's convenient to have another trick up our sleeves for measuring discharge. And this is dilution gauging. It's a better choice for streams that are too small to measure with a current meter. What it involves is upstream injection of a conservative tracer, meaning a tracer that has no sources or sinks along a reach. Usually this is a salt tracer of known concentration, and it also involves sampling the concentration of that tracer further downstream. Discharge is solved based on principles of mass continuity or mass conservation. The upstream injection of the tracer may either be continuous or as a single slug. In this class, we'll be using a single slug or a single drop of the tracer into the stream. However, it's worth noting that continuous injection upstream is most accurate, but it can be a lot more difficult logistically to set up. So some site requirements for dilution gauging are that the tracer should be completely mixed throughout the stream. Usually this requires an injection about 50 feet upstream of the location where you're making the measurements. There should be no inputs of water between the injection site and the sampling site, no losses of water between those two sites. There shouldn't be any eddies or backwaters that you can see, and if possible, the flow should be converging upon your measurement point rather than diverging. So let's just sketch out, first of all, the continuous injection method, which is the highly accurate injection method. So let's say we have our stream surface. We have an observer down here. So this is our observer who's also sampling the concentration of the tracer. And then some distance, at least 50 feet upstream, we have the tracer being injected into the stream. So here's our reservoir of tracer. Oops, I didn't mean to do that. So here's our tracer. So if we're using a salt, all streams have some salt concentration, even if they are freshwater. It's some non-zero salt concentration, and this is something that we need to account for. We call this C0, or the background concentration. We also have a discharge of Q upstream, and this tracer is being injected into the stream at some rate, which we'll refer to as small q. It has a concentration C1. Now, downstream, where the observer is collecting samples, the concentration of that tracer is going to be somewhat diluted, so we have yet another concentration that we're accounting for in these equations, CQ. And the discharge downstream is going to be equal to the discharge of the stream, plus the rate at which the tracer, the liquid tracer, is being injected into the stream. Now, just to keep track of units, we have both small q and q having units of volume per time, whereas all of the concentrations, I'll just refer to those as C sub x, have units of mass per unit volume. Okay, so I'm going to define, first of all, the flux of the tracer. In dimensions of mass per time as being equal to the concentration of the tracer, and I'm not putting a number here just to keep it general, times the discharge at that particular location. So now if we apply conservation of mass, if the stream is flowing here from right to left, all of the tracer that is injected at this point here has to eventually pass by the observer. And so we could write an equation which is the flux of the tracer at the point of observation, which is just equal to C2 plus big Q times big Q plus little q, has to be equal to the flux that we're putting into the stream at the upstream location plus the flux of the background concentration of the tracer. So if we rearrange this, and this is just called a two-component mixing equation. So if we rearrange this, we can get C2 times big Q plus C2 times small, or let me back up a little bit. C2 plus big Q minus, you'll see why I'm writing it this way in a moment, minus C naught times big Q equals C1 times little q minus C2 times little q. So now you'll note we have all of the big Q's, which we're trying to solve for, on the left-hand side of the equation, and so we could just divide through by C2 minus C naught to end up with little q times C1 minus C2 divided by C2 minus C naught. Okay? And so we have now solved for the discharge of the stream. So let me just draw one more picture on here, which is what it would look like to the observer who's sampling the concentration of this tracer over time. So what we want to plot is C2 versus time. And at first, before the tracer reaches the observer, at the very beginning of the experiment, the concentration is just equal to the background concentration, or C naught. Now, once the tracer has been put into the stream, it will disperse just through diffusive processes and through the processes of different streamlines having different degrees of tortuosity. So eventually, the concentration will gradually begin to increase, and then it will increase more rapidly, and then that increase will taper off, and you'll reach a steady state or an equilibrium. And this equation that I've written out here requires that the C2 that we're using right here is sampled at equilibrium, okay? So sample C2 at equilibrium. Now this curve that I've drawn here has a particular name, which is breakthrough curve. So this is actually a fairly simple equation based on conservation of mass, but it does have some disadvantages. And one of those disadvantages is that if you're making these measurements over enough time for the stream to reach steady state in terms of the concentration at the point of the observer, then you need a large reservoir to store the tracer. The injection also needs to happen at a constant rate, which can be something that's a little bit difficult to achieve in practice. And so there's another solution to performing one of these types of analyses, which is known as the slug method or the gulp method. It's got kind of a funny name, but it just basically involves dumping a known volume of tracer at known concentration into the stream at an upstream location. Concentrations downstream are then measured at regular time intervals until the tracer is no longer detectable. So the experimental setup is like what you see here. So we have our observer standing downstream. The flow is in this direction from right to left. We have a background concentration upstream. Downstream, the observer is measuring the change in concentration over time. And then here we have our reservoir of tracer again. So here's our tracer. But now instead of a continuous injection, it is just a single dump into the stream. And this slug that's introduced into the stream has concentration C1, and it has a known volume V1. Okay? So again, we can apply the conservation of mass, because everything that we dumped into the stream upstream has to pass by the observer downstream. So applying conservation of mass, we get that the mass of the slug, or just this dump into the stream, is equal to the stream discharge. And here we're assuming that because we just dumped everything into the stream at once, the small q is practically 0 compared to the size of big Q. So we only have to worry here about big Q. And so the mass of the slug is equal to this big Q times the difference between the measured concentration and the background concentration times each interval of time over the full duration of the experiment. Okay, so the summation here is over the full duration of the experiment. We could see how this works out because big Q has units of length cubed per time. This is a 3. The concentrations have units of mass per volume. And then time, the time interval has units of time. So this crosses out, and we're left with mass. Okay? So if you assume that you don't lose any mass and that you're able to sample all of the mass that comes downstream, we could rearrange this. Or rather than rearrange, we could rewrite the mass of the slug as just equal to the concentration of the slug times the volume of the slug. These are the things that we measure. And again, this equals everything that we already had on the right-hand side of the equation. So now we could rearrange this to solve for Q. And in this way, we get Q equals C1 V1 over the sum of C2 minus C0 times the time increment. So all of these things are part of the summation. Okay? So what the observer sees in this particular instance is change in concentration over time. So initially the concentration is the same as the background concentration C0, and then it increases. It will plateau for just a little bit, but then it will go back down again. Okay? So this is, at the top, this is known as the CEQ, or the equilibrium concentration. You might not always achieve this, depending on the size of the slug that you dump into the stream. But then these other parts of the breakthrough curve have different names. So this is called the rising limb of the breakthrough curve, and this is called the falling limb of the breakthrough curve. Okay? So I've already given that solution. Go through that slide. We're going to end here. This concludes the material that you'll need in order to answer the questions on the Strawberry Creek discharge exercise. Okay, bye.